Alrighty, so let's go ahead and start doing some review. And I do try to obsessively review. I hope you're not too bored with the constant reviewing that I do, but especially for quantum, I think it's a very good idea. And I was just thinking, I don't know, folks, you probably recall. Remember how I mentioned when we got into the quantum area? Hell, I think I even said this last semester. The thing about quantum is it's like you have to simultaneously know like 5 different things. Yet I'm trying to explain those things one by one without you knowing the other 4. And that's just unbelievably awkward. And that's one of the reasons I'm always saying if you feel like a little flummoxed, watch the videos and whatnot. One of the reasons I tend to constantly review. So anyway, so let's review flat potentials. So, this is a silly flat potential, no potential at all. And the free wave problem, the electron in the infinite universe with nothing else. Hopefully you're sick of this. I actually don't mind you being sick and bored of things because that means you probably got this down, which is way better. I only linked. I just realized again. I uploaded the extra hour video. I uploaded it to YouTube on Saturday, but I didn't link it to the website till like an hour ago, so sorry about that. The second hour, which you don't need at all, but I would recommend this, because why else would we do it? I did show how you solve the second order differential equation, hint that is the Schrodinger equation. Schrodinger equation is a second order differential equation, and how you can solve the Schrodinger equation. It's a second order differential equation because of the kinetic energy operator. And only with the kinetic energy operator, if that's all you have, that this is the solution. You watch me flummox towards the end. It's only 35 minutes because the lecture was only 35 minutes. But anyway, so you can see how that's done. And hopefully you're sick of this. Okay, free wave, that's the answer. Last time we also talked about how you have to know a little bit more, right? Fine, but so what? You have to be told something like, what is the energy and where's it going? Remember that I can't just like give you a test with one question that says, hey, do some quantum mechanics, right? Well, on what? There you go. On what? What's your model? What's your Hamiltonian? Just like last semester, I have to give you at least what's the mass of O2, what's the size of the piston it's in, how much does the piston expand. There's a certain baseline of information you have to know or you can't do anything with. So be conscious of that. If you're looking at the exam and thinking, wait, I don't know enough, I hopefully was a bit more careful than that. So let's say that, for example, I say it's a right wave. And again, this is, I was thinking whether I would give the exact same example I gave last time. I decided to do that. In which case, you know that if it's a right wave, then that's the left wave, so no. And you know that because when you apply the operator on the wave function, you get a positive number, and that means it's moving to the right. And I did what I did last time. I forgot the little a. And a at this point becomes a normalization constant. But you also know that that's the reason that this is actually a weird problem is that the normalization constant is actually 1 over the square root of infinity, something that people almost always try to gloss over when introducing quantum for the first time, but I also, so maybe to my discredit, I try not to do that. Anyway, so we talked about that last time. P squared operator gives h bar squared k squared. Sorry, I need to write this out in the eigenvalue way. A is the ikx. Okay, and then therefore you know kinetic energy, which ends up being very easy. Just divide by 2m. There you go, now you know the energy. We also talked a little bit about uncertainty principle, how you actually have no uncertainty in the momentum, and that's because of the setup. God creates a particle and throws it with this much energy. It's only kinetic energy. So if you know the kinetic energy for certain, you have to know the momentum for certain, but you also don't know how fast, you don't know where it is. You have no idea where it is with absolute uncertainty. And anyway, we talked about that last time. Now you can also think in terms of like, in case you're, what's going to be the test? Note that I basically asked everything I humanly could. I actually did have, didn't I do the flux operator on the homework? I think I did that with you guys, right? Anyway, there was an operator, a flux operator. I thought I had you do that. But basically, you're seeing everything I could ever ask. Okay, so, I mean, seriously, that's really about it. And hopefully you're bored with this. All right, next thing. Next thing was particle in a box. And what's funky about this is that the wave function, it's because we're on flat potentials, the answer is always this. It's always this. But just like the free wave, you have to narrow it down. There's stipulations that are made. Sorry, that K wasn't perfect. There's stipulations that are made, and those stipulations then make you do some modifications, and then you can apply operators. I don't know. There's kind of a lot of things you can do with this. Okay, in this example.
Isn't that supposed to be negative?
Yes, thank you. I did that last time. Thanks for catching that. So, boundary conditions. Right now that we step away from what is hopefully like a childlike example, now you enter the world of stipulations such as the wave function has to be 0 sorry, look how I put that. At x equals 0, the wave function has to be 0, and therefore a is equal to minus b. And something I told you that the wave function at that point, you know for certain that it is, I don't know what's wrong with me today, it's a sine function it has to be. Okay, what else do we do? Then we also know that the wave function at x equals L has to be 0, and therefore we now know that the wave function is, what you actually get out of this is what k is, and I'm just going to write this down, n pi x over L, where n is 1, n equals 0 is actually works, it just doesn't mean anything. That's like for a particle that's not actually there, for an empty particle in the box. Okay, so that allows you to draw wave functions. You can plug this in the Schrodinger equation and get energy, which is n squared something, I actually already forgot what it is, over m over L question.
What would the symmetry look like for a cosine?
So you're wanting me to tell you homework answers. So now, what I have you do on your homework is, because I don't want you just like, not that I'm like trying to accuse you of anything, it's just, I don't want you just rewriting what I do in class. That's terrible, but to get you to really get this on your own, what I did was on the homework was I recentered the particle in a box to 0. So it still is L long, and so there you go. And so I'm forcing you to work with that. Now, sine, so here's the thing. So how would you do that? Well, you have stipulations. You solve this by stipulations. You just have different ones. At x equals minus L over 2, the wave function is 0. So what does that mean for A and B? It means it'd be equal, right? So now does that e to the, let's solve it, e to the I k L over 2 is plus b e to the minus I k L over 2 is equal to 0. So a e to the I k L over 2 is equal to minus b e to the minus I k L over 2. Now, what I'm pretty sure happens is if you do this, I need to use some online resource because I'm blanking out. E to the minus a over e to the a, what would that be equal to? This looks like it's, yeah, I'm just squaring it, aren't I? Huh. What, no, because I screwed up. Well, no, that doesn't really do anything, does it? No. Well, the thing is, well, I feel like I'm choking here, but Well, I know that A has got to be equal to B, so this has to be equal to -1. So regardless, yeah, sorry, I just don't know enough math off the top of my head to, I just need to Google. I'm sure there's an identity on this. I know there's an identity on this, but what you end up with is A is equal to B, and therefore the wave function has to be cosine kx. Besides, you can, in all honesty, you can just kind of look at it, right? I mean, it has to look like this. So the max amplitude is at 0, which sine literally does not do, cosine does. But now let me guess, the question is, so you mentioned what about cosine? I think I preempted you a little bit.
I just asked like the symmetry for cosine, and you answered it.
Well, now here's where, this is where the problem gets a little funkier. Let's do the first excited state. Now what's that? It's not a cosine anymore, is it? Right, so what happens is, you end up with an odd even problem. So like n equals 1 is a cosine, n equals 2, the first excited state is a sine, n equals 3 is a cosine, n equals 4 is a sine. So that's the answer to some of the homework questions, by the way, is that happens. Now you see why, when I cover this, you see why I center at 0 to L in class? Because this works all the time, right? So it's not like confusing, right? I don't do it this way. I don't do it this way because look at what just happened. Now I want to emphasize, what you get for your analyses here is the same as here. This is the same problem. This is just a weird practical thing that happens, and that's sucky, but it's still the same problem. And so, now one reason I did this is, I can do this here, or you're doing it on your homework. What's this? Now the reason I centered the particle in a box on your homework at 0 is because what is this? 0. Yeah, right. So this is unbelievably easier. And what's this? Now again, this is irrespective. We've gone over this a couple times, and it was on your test. Now remember, this thing is trapped in this box. Yeah, the average momentum is 0. Right, now remember, because what if it's not 0? If it's plus, it's h bar k. For that to be true, on average, it has to get out the box. It has to, maybe it hits the wall and bounces left and goes right and bounces back, but every now and then it has to get out, or that's what it would have to do to have a positive average momentum, and vice versa for negative. But if it's trapped, what happens is, it does have kinetic energy, so it is moving to the right, but it moves to the left just as much as it moves to the right. How else could it stay in this box otherwise? And if that's true, then the average momentum is 0. Okay, now when it comes to answering your homework question, then you've got to do some online integrators and do this stuff. And unfortunately, that is a lot of algebra, no doubt. It's not, I'm not hopefully making this class too trivial. It's going to probably take about an hour to wade through all the algebra, and there's some simplification you have to do. Because what you end up with is, and again, this fits in, one reason I'm actually glad that this was asked, is that you can then answer questions such as this, which I talked about in the free wave. This looks like the uncertainty in position, uncertainty in momentum. Remember that what I've just written here are the standard deviations. And when I'm talking about the position uncertainty principle, you have this relationship. Now what you do on your homework is, you can see why I centered it at 0, because this gets way easier. It gets way easier. And then you're going to show that actually, I think on the ground state, you get h bar over 2, and for the excited state, it tends to be a little bit bigger. So there you go. Now again, one thing about this is notice that what I've done is I've given a model problem. I whittled through the solution. I choked a little bit here, but it is cosine. I'll try to look up how to use these. When we did this here, it was very easy. I know I can do it here. I just kind of choked there a little bit. Sorry about that. I'll figure that out. But these boundary conditions give us the wave functions. And once you have the wave functions, then you can do energies, and then you can do uncertainty principles. I'm not sure what else I could do at this point. I'm sure that, I mean, there are, as I mentioned, I think off the top of my head, I know 20 operators off the top of my head. I don't know that they necessarily apply. I don't think there's any angular momentum here, but there are a bunch of other operators I could ask, and maybe I'll find one and put that on the test, and I'm sure it's just taking a derivative of a cosine or something. But there you go. So again, model problem, whittle down the wave function, then use the wave function. Any other questions? So anyway, dropping test tense, and as usual, it's a little too long of going that I meant. But if that helps in your homework, if you're dealing with your homework, you're really behind, that's not good. Okay, what we're going to do today is follow through on the step potential. And we're going to get into a decent amount of algebra today, by the way. And this is not going to be pleasant. It's not terrible. It's about 6, 7 steps, so you may want a page set up to do this. Now, where we have a little funkiness here is that you've got to separate your wave functions in two now. So that's where this gets a little funky. You got a wave function on the left, a wave function on the right. And the wave function on the left, you weren't here on Friday, but anyway, I did post the first video rather soon. There again has to be a setup. Even to get to this, we actually have to have a bit of a setup, which is to say that the great turkey in the sky created a universe with a single particle and a barrier, and threw the particle with a certain amount of energy at the wall. Now that's why this wave exists, because that is, Apollo or Athena, who created the universe, throwing the particle at the barrier. But since there is a barrier, it's going to bounce back, and that's where we get the B wave, the reflection with a freaking minus sign. If it goes over the barrier, so again, the thing that's funky about this is that you have two different wave functions, and the conditions that allow you to solve this are going to be smooth and continuous, and that's what we're doing. If it gets past the barrier, it will still move to the right, but there's no reason to move to the left, and that's why I'm not writing a d e to the minus k through x, which brings up another point, which is what is k1, k2. K1 is, and you've seen this enough times now, hopefully this doesn't bother you, it's the momentum, and work through the units, square root of 2me over h bar squared has units of momentum. And where it gets a little funky on the right is this. V minus E. I want to say E minus V. If E is 2, no, E minus V. Maybe I should be looking at my notes, that might help. E minus V. So, anyway. Okay, so I made a lot of noise early in this class about how when you have the flat potential surface, e to the ikx plus e to the minus ikx is the general solution. It turns out that that's always true for the flat potential, even if there's a flat potential with a barrier. So I was a bit snarky with the particle in the box and said, oh, it still works because between 0 and L, the potential is flat. But really, I was kind of hiding something because I just don't want to overload you. This is always the solution so long as the potential is flat, even if it has a step to it. It's still okay. Okay, so anyway, I'm still reviewing, and now we want to solve it. Now recall that, okay, so what do you want to do with it? I don't think I'm interested in solving momentum or an uncertainty principle, because we've kind of done that to death. Instead, what I'm going to try to do is, again, setting up these models, so what? What I want to do is question who is making toast right now. Wait, so seriously, someone like right now actively making toast? If you are, yep, please stop, because it's really it's kind of like getting smoky in here. So anyway, well, folks, if we have seriously, this is kind of getting close to like the fire alarm going off. So if that happens, then we'll all have a break. But anyway, let's see how long we make it. So having set up this problem the way I have, I mentioned last time that B over A is related to the reflection, but unfortunately it's the square root. And the reason that is because, remember, wave functions don't mean anything. You have to take the absolute value and square them, and then they're meaningful. So let me actually put it this way. Let's put it this way, B squared over A squared, and that's percent reflection. Now, again, remember, that's the Born interpretation showing up. Born's interpretation is that a wave function squared is a probability distribution. Remember, what is the number one way that you mess up questions on the final? You get a Maxwell-Boltzmann distribution and then square it. No, don't square it, it's a probability distribution. Or you get a wave function and don't square it. No, you're supposed to square it. A square is a probability distribution. Now that fact is kind of showing up in here. All right, now so what? Okay, now here, let me just wipe this out for now. Now this is going to be, again, a little unpleasant. You might want a page set up for this, because I'm just going to do a mess of algebra. And, I don't like doing as much algebra as I have no choice but to do, but regardless, what we have are some conditions. Okay, let's do continuous. Okay, so the wave function has to be continuous at x equals 0. And that means that, let's see, I have a e to the I k1 0 plus b e to the I minus I k1 0, which are, that's a plus b, is equal to c e to the I k2 0, not that that matters, and therefore a plus b is equal to c. And that means that the two wave functions touch each other. Remember, you can't have a discontinuity. So remember that continuous and smooth are the stipulations that wave functions have to follow. It's kind of similar, before I had to have the wave function 0 at 0 and L. This is kind of like that. I don't have exactly the same stipulation as stipulations smooth and continuous. Okay, so now let's do continuous in region 2. And this is where it's a little bit, now I definitely have to look at my notes here. No, wait 1 second here. I'm making a mistake here. No, sorry. Sorry, I didn't have enough in class, before class. I had that call from Argonne. Let's do smooth. And that means that the derivative in region 1 is equal to the derivative in region 2. Okay, so again, if there's to be a seamless transition from region 1 to region 2, which there should be, this is only one particle. There's no bends to these wave functions. Not only do the wave functions have to touch each other, they also have to have the same derivative, smooth and continuous. I hope that's rather obvious. Okay, so not too terrible. I know enough to do the derivative. And again, the position is. See, notice I almost choked there. I almost wrote e to the I k1x. No, it's smooth and continuous at x equals 0. And I almost forgot a minus sign. So for some reason every year I always kind of screw up something different, something kind of, systematically. And today, in this year, it seems that I'm always forgetting that minus sign. K2, 0. Okay, now let me check my notes because I'm just not, okay. All right, simplify. K1A minus K1B is equal to K2C. Okay, now, I told you, this is gonna be funky. I'm gonna be going back and forth. This is not, it's all algebra. You can do algebra, but it's, anyway, it's just a bunch of, okay, so A is C minus B, and therefore K1 C minus K1B minus K1B is equal to K2C. And what that allows me to do is I'm going to whittle, let me just write down the algebraic result. If there's nothing to this, you can see I can bring over the other term, so K1 minus K2, and factor the C term out. And then I can bring 2K1B over to the other side. I'm just going to bring B to the other side and then divide by 2K1. Okay, so there we go. Okay, why did I do that? It's because, just because I can. So what I'm going to do is I'm going to substitute that into here. I love this. There we go. Solving multiple equations for multiple unknowns, right? That's what I'm doing here. And I'm trying to get, remember, I'm trying to get to B over A. Yeah, B over A. Now, to do that, what I'm going to do is, notice that I'm going to have A as a function of C. See the strategy here? A is a function of C, and I've got B as a function of C. So when I divide the two, I should be set. All right, so anyway, that's, I told myself I'd always try to make sure I explain what the heck I'm doing. I maybe do that slightly better, hopefully. Okay, so I got C minus, how do I want to do this? I'm going to actually break this up. It'll make the algebra a little bit harder, a little easier. Okay. Now, then what I can do is I can solve a common denominator. I can multiply this C times 2K1 on top and bottom. So I've got 2K1C. And now they've all got a common denominator. And I, wait, what did yeah, you see what I did? Minus B. So minus K1 minus plus the K2. See that? See how I screwed that up? Minus this changes that sign. So I messed that up. Sorry about that. It helps. I just really need to look at my notes more often. That would really solve all the problems. And then 2K1 is a common denominator. And then I can simplify this. Let's see, what, K1, yeah, right. So this ends up being K1C plus K2C over 2K1. Okay. Now again, I'm trying to get B over A. Now I need to go to another board because I'm not done yet. I'm not actually even close to being done. And nope, I didn't raise it enough. Okay, so hopefully you can see this in one continuous transition. So I'm just going to keep going down. Okay, hopefully you've seen that I basically got this part done. Someone can keep an eye on time as well, because my watch is still broken. I didn't have it time. Oh, and my license is about to expire. Oh, the cat's in the hospital. My foot hurts. I have to go to work on tomorrow. I don't know how I haven't eaten in 5 days, too. Anyway. Okay, so now what I can do is solve B over A, and then I can square, and then I'll square them later, but this is good enough. Okay, so what have I got? I've got K1 minus K2. Obviously the C's are going to cancel. Now multiply that by 1 over A. Oh, look at that. Okay. For B over A is, I got this right. K1, yeah. K1 minus K2 over K1 plus K2. Okay, there you go. Now, what this does is it sets up, it means that everything depends on, let's see, what are the K's? So if you're looking at this thinking like, well, what the heck is that? Is that the answer? The answer, that is the answer, because K1, let me just write this down again, is 2me over h bar squared. Now remember, I have to tell you what the energy is. When when Apollo or the Great Turkey created this universe with the barrier and the particle in it, that creature threw the particle at the barrier with a certain energy, and the barrier was also defined. So you know what these are. You know what these are. You have to have been told this. So now that so these are numbers, and now that you have numbers, you have that number too. So that's the idea. Now, that's all fine and good, but you know that we like to look at these as functions and figure things out from there. Now note that this is the square root of reflection. I might just leave it like that. And 1 minus b over a is the square root of transmission, because of course reflection plus transmission is equal to 1. And this ends up, let me just write down the answer, 2k2 over k1 plus k2. Right, so there you go. Ta-da! Probably one of the longer things probably the longest thing we've ever done. Again, just remember, it's just a bunch of algebra. It's a lot of algebra. So you can do this. I'm probably not going to put something like this on the test. This is, I mean, what I just spent 20 minutes doing this, and I have a good set of notes. Supposedly know what I'm doing. Okay, so, Jesus. Scared me. Okay, so given the nature of this problem, I've now done just about everything I might ever want to do with it. And so now I want to do is just analyze the aftermath. Look at reflection transmission, and something I've kind of been failing to do is to tell you what is it actually relevant for, which is kind of hard because like in 342, it's like at no point could I say, oh, this is like your car engine, or this is why an airplane flies at 30,000 feet. When it comes to quantum, it's all about like electrons and stuff like that that you don't see. Unless you've been hit by lightning. And so it's a little abstract. But so what I want to do is analyze these things in functional form and give you some examples of why this is actually relevant. Okay, so first thing to note is let's do some limiting cases. And one of them is, let's say, it's an easy target to go for, is, so we can think of 3 limiting cases. Okay, if the energy is the same as the barrier. So the Great Turkey in the sky we have a 1 eV barrier, and remember you're used to electron volt energies. Those are good energies for molecules. The Great Turkey has a 1 eV barrier and threw the particle with 1 eV of energy. What happens? Okay. If E equals V, tell me. You should be able to say something like very quickly. That's 0. Okay. And the wave function, okay, and so the wave function at region 2 is equal to what?
C.
Equal to a number. Right, it's equal to some kind of like normalization constant. Now, the thing about that is that it's flat. Okay, so what that really means is practically is that this is what's going to happen. Let me tell you what I'll draw. I'll draw all the limiting cases. This is just one out of 3 limiting cases. I always have to start. I have to kind of do this backward for various reasons. Okay, so that means you're actually running into this scenario here. It's actually not going to penetrate. And how do I know that? Now let's see. Okay, so the wave function is a constant, so I had to draw a straight line. But now let's look at the transmission. What's the transmission? 0. Okay, right. The transmission is 0. That's how I knew that the wave function is actually completely flattened like a 0 type of way. Not. Don't write this down, but you know what I could have done is I could have done something like this. No, that's not, you can't even, no, that doesn't work. It has to be 0. That's because the transmission is 0. Okay, now, this is the one case that kind of makes sense, which is that, now imagine like okay, so we're playing handball, there's the wall, right? There's the wall. Neil had the ball and I threw it with just enough energy to get the ball over the barrier. Here, let's draw it like this. Kind of like handball. Okay, so a person threw the ball, just enough energy to sit at the barrier, sit at the top. Where does it go? Nowhere, right? It gets stuck. It gets stuck because it just has just enough energy and no more. So it doesn't go further. So this kind of makes sense, right? So that would mean the transmission is 0. And from a practical standpoint, I can tell you, and again, I don't know that you, at seeing this for the first time, would be able to figure out that the wave function is actually like this, that it actually just goes straight to 0. I wouldn't expect you to quite have enough experience to be able to know that, but so I'm telling you that. That's how it goes. Relatively simple. I'll tell you what, now let's see what else I want to do. I want to do, I guess it's a little bit more interesting to say if, what I want to do. Okay, let's do energy. Energy is less than V. Okay, in that case, what happens to this? And this is an issue that came up in the second hour on Friday. What happened? What's the consequence there? We always want to look at the K's because that's where all our answers are. That's imaginary, right? You see that? Right, E minus V is a negative number. I've got the square root of the negative number. Therefore, it seems like everything is really about the right half. The left half we don't seem to be too worried about. Okay, I still got this constant, but I've got e to the I, K2, which is I, square root of 2me, V minus E. I reversed that, by the way, that's not a mistake. And I did that because I took the square root out. I took the minus sign out of the square root. And therefore, it's e to the minus. This isn't quite right? It's a little bit more complicated, but anyway, it's an exponential decay. Remember that e to the I, in case you forgot about this, e to the ix is wiggly. That's a wave. E to the minus x is an exponential decay. All right, so what happens there, again, I always have to start on the left side. Very slow and deliberate. Okay, look what happens. So I have the wave function reaching 2, it just kind of exponentially dies off. Notice how I drew reaching 2? Is that more or less energy than this case? What do you think?
Less.
Less energy, right? Because it's not as wavy. Wavy is momentum, momentum is energy. So I drew it less wavy because of because it has less energy, and that's why I didn't get over the barrier. Okay, here's a cool thing though. Now this is where we start to see things. Now again, this guy hopefully makes sense, but what the hell is that? You see there's a little area? There's a little area into the barrier. Now this is where you're starting to get into, for the first time, you're seeing some weird quantum mechanical stuff happening. What happens is, okay, I'll draw this one on bottom. Okay, so I threw the ball at the barrier, and let me reverse perspective here. It didn't quite have enough to go into the barrier. It didn't have enough to go over. It didn't even hit the top. But what I saw was the ball, there's a glitch in the matrix. I saw the ball go into the barrier before it bounced back out. Now you may think that, well, the ball just kind of got smushed. No, it went into the barrier. And that's because we're all actually attached to the machine world. But anyway, but I don't want to talk about my theories in that regard. I've been told by the psychiatrist not to. So anyway, God, that's a terrible drawing too. That bothers me. Anyway, bothers me more than my machine theories. So there we go. Okay, so that's what happens. The ball actually partially goes into the wall. Now, maybe some of you heard that in quantum mechanics is weird because the cat's alive and the cat's dead simultaneously, which we know is not true. That's also part of your homework. What that wave function means, I'm answering some of your questions in your homework. That just means that there's a certain probability that the cat's alive and dead, not that it is alive and dead. When it comes to this guy, this is the part where it says you might walk partially through a wall, through a door. Not really. It means that there's a certain probability you might. It's just the probability, by the way, is smashingly low so that you don't actually ever do it. So again, something that's very quantum mechanical is says that there's barrier penetration, which would never happen in what we call the classical world, right? A ball would never do that. Okay. Now I'm going to expand upon this with a different potential. What I'm going to do is I'm going to do a potential where the barrier is finite, and I'll let the barrier drop back down to 0 before the wave function tails off. I'll do that. Maybe I'll get a little bit into that today, but maybe not. So now the third case is if E is greater than B. Not much to say there. Let me just draw that as accurately as possible. And again, I do have to really think about that. Be very deliberate. Okay. Some pitches in the way, but anyway. Okay, so there we go. Sorry, I'm kind of overlapping. Okay, so notice what I've done. A couple of things. Notice that the momentum is more or less, the wavelength is more, you have a longer wavelength, but that's less kinetic energy. When it does get over the wall, it lost some energy to the potential, so it moves slower. Again, that's actually sensible, right? Now notice that on the left side, I drew this with more waviness than either of the other two cases, and that was intentional. Notice the amplitude. Notice the amplitude. Notice I drew less amplitude on the right side than the left. Now that's for a reason too. And that reason is, okay, this is where this gets really, really strange. As much as this doesn't maybe seem too weird, but it actually is. What's really, really weird about that top case is when you plot. And now remember, there's a handout on this one. And I do all this, by the way, in the handout because, as usual, this was really, I know that I may mess up a minus sign. I know you may mess up a minus sign somewhere. So I have all of this worked out on the handout. What I also have worked out on the handout is this, where I plot percent reflection, which is this quantity. Now remember that, so what I'm doing is giving you the absolute value. So I am so used to, I've done enough quantum mechanics that I know when I see an absolute value squared, I don't just say, oh, square it, or just, oh yeah, absolute value. I know to put down the thing, complex conjugate times the thing, right? And we've gone over this a bunch of times. It's just that, remember that whenever you see an absolute value squared and you're talking about quantum mechanics, you need to be putting this down immediately. Okay, so what I did was I plotted that. Of course, the maximum is 1, the bottom is 0. And I plotted that as a function of barrier.
Isn't that supposed to be A instead of C?
B, yes, A. Thank you again. I feel like I know this so well, I just start writing things. Right, thank you for catching that. Okay, and then I've gone out to as far, I didn't really do this to scale very well. I probably wouldn't want to actually. 5E over V0. Okay, now the percent reflection is 100%. Now remember, that's reflection. I know you probably thought, oh, I bet it was 0. No, it's 100% reflective if the energy doesn't, if there's not enough energy to get over the barrier. even up to, exactly up to the energy of the barrier for all the reasons we said. Okay, now classically, if the ball gets over the barrier, off it goes. It may go very slowly if it has just a little bit more energy, but it does go. And that means that you would expect this behavior. So this is the classical behavior. But this is not what you get. Quantum mechanically, this is what you get. It has enough energy to get over the barrier, but sometimes it bounces back anyway, kind of like a comedy that you probably laughed at more when you were in 5th grade, where somebody's adding something to a mailbox and it pops back out. And again, when you were little, you thought that was hilarious. I still do. So then if you do percent transmission, so this is reflection, and 1 minus that, of course, is percent transmission. Sorry, again, my use of the board is not great today. Percent transmission is just the exact opposite of that. Well, it's not the exact opposite, it's just a reflection. Okay, so there you go. Again, this is actually really, I hope you're not thinking, oh, whatever. This is really not, this is absolutely should not be happening, right? Up to here, this isn't weird at all. Up to here, this is really, really nuts. If the ball has enough energy to get over the barrier, it does so unless that barrier is like some electrostatic field and the ball is an electron, in which case, no. It may or may not. Even up to about 5, even if it has 5, even if I throw the ball 5 times higher than the wall, there's actually still a decent chance the damn thing comes right back at me. And again, that's really weird. But we see that kind of behavior quite often. And I guess I'm kind of out of time, so I won't talk further, but yeah, I'm out of time. Let me just point out what we're going to do. And when I show you things that actually matter, like actually apply this stuff to real things, what we're going to do is next time we're going to do this barrier. And what you see is this behavior. What you see is this behavior. This is called tunneling. Yeah, have you ever heard of tunneling? This is when you walk through the wall and actually get to the other side. There are molecular examples of tunneling, and we actually see them all the time. So next time, I'll finally maybe make this actually relevant to the chemical community. There you go.